Now that you have finished the first video on fundamentals, we'll be able to move on to some really important ideas of sample space, probability distribution, which is hugely important, and will continue to come into topics all the way through inferential statistics, and of course expected value. What we'll do is we'll continue using the same example we did in the first video. We have our quiz of 15 multiple choice questions, each question having 5 options. When we talk about sample space means the set of all possible outcomes. So when we are talking about a multiple choice quiz with 15 questions, right, what are our outcomes? Well, you could get all 15 right. Wouldn't that be great? You could only get 14 right, or 13, 12, 8, 7. What's the whole range? Well, you could get down to 0. It doesn't make sense that you could go negative, and it doesn't make sense that you can go bigger than 15. So we have a very nice defined set of all possible outcomes. And we can list, and I'm going to use the TI-84 notation, because you would usually put this in maybe your stat lists. So in L1, you might list what are all the possible outcomes. So you could have 0 right, 1 right, 2 out of the 15 right, 3, 4, 5. And I'm not going to do all of them, but you can of course go all the way up to 15. These are all your possible outcomes. And as we already learned in the first video, for example, what's the probability of getting 5 right? We know that's 0.103. Well, we have all these other possibilities in our sample space. We could actually figure out what those probabilities are as well. And as I said in the first video, we spend an awful lot of time figuring out how to calculate those probabilities. It's not what I want to talk right now about, so I'll just provide these to you, because once we have all of them, I'm interested in this next concept of probability distribution. So here they all are, and you can now see what we were working with before, this 10.3% for an outcome of 5 correct answers, in sort of a larger context. Say, well, is this the most likely outcome? Well, no, it seems like maybe getting 3 correct is the most likely outcome. It's the biggest probability. And it kind of drops off in both directions. Now, this number, this is what gets displayed in the calculator. Just a review of what e to the negative 11 means. Remember, that's exponential notation. It means you need to move the decimal point, which is right here to the right of the 3. 11 decimal places, negative means to the left. So you go, 1, 2, 3, 4, 5, 6, 7, 10, 11. So is that going to be a very big number, a very small number? And it's a tiny number, very small. So which makes sense, because you think if you have a 20% chance of getting a guess correct, what's the chance of getting 15 in a row correct? Well, that's going to be a really small chance. I mean, you would not expect that to happen very often. So, correspondingly, this is a very small probability. And you'll notice actually, given a 20% chance of success for the individual random event, would you expect to get all 15 wrong? Well, actually, no. That seems like it'd be a kind of unlikely event as well. I mean, you'd expect at least to get 1 or 2, or I guess maybe 3 of them right out of the 15, if you're purely guessing. And so this is really kind of should make some intuitive sense. The fact that it's 3, that's the most probable, well, that's because the event, right, the guess of each question isn't 50-50, right? It's 20-80. So there's a bias, you can kind of think of it, towards failure, right? It's more likely you're going to guess wrong than you're going to guess right. So, halfway to 15 would be 7 or 8, right. Well, if it was a true-false quiz and you had a 50-50 chance, well, yeah, you'd expect to get about half right. But it's not. You'd only expect to get, less than half right, since the probability of success is less than 50%. Now we can say, well, what is this probability distribution that I keep talking about? I mean, we see this, this really is the probability distribution, right? Because it's a sample space. These are all the probabilities for all the possible outcomes, right? This is the distribution. But when you talk about probability distribution, usually that means the graphical representation of the sample space. And this is usually done, not always, but usually done as a histogram. You can see all of the concepts we did earlier in this course are coming back. So if we were to draw this, as your x and this is as your y, or your frequencies, you would have your histogram of probabilities. Here's our histogram. Right, and you can see this, really is a nice visual representation of this data. We can see the most probable outcome is 3, right, getting 3 correct. Notice for a moment, what is that most probable outcome? It's actually only 25%, which is sometimes confusing. Like, well, wouldn't you expect the most probable outcome to be, something bigger, like 50 or 75%? We're going to come back when we start talking about expected values. We're going to return to that concept. Notice that it kind of comes down. These are not 0. I tried to make this a little bit bolder, but they're just very small, so you can't even draw boxes for them. And here's our, 3e negative 11, which is just minuscule. So, these are almost indistinguishable from 0, but are non-zero. We can start employing all the things that we did with histograms before. For example, what shape does this have? Right, well, this is a right skewed histogram. Like I said in the other video, right, we can actually get standard deviation and all kinds of measures of variation. Everything that we've done previously will actually apply to these distributions. Now we'll talk about expected value. Now we want to make sure to distinguish, because before we talked about expected occurrences. Right? So this is different, and we'll do a little compare and contrast here. So when we talked about expected occurrences, that was answering the question how many of a certain outcome will occur. Now here, when we're talking about expected value, we're talking about which outcome would we expect to happen. So we could ask a question like this. If you randomly guessed on the quiz, what result would you expect to get? Another way of asking this would be, how many would you expect to get right? I chose not to use that phrasing because it might be confused with this, how many. How many you get right is really asking, what's the result? So you do have to, not be too hung up on words, but think about the meaning, right? Are we talking about outcome, or are we talking about how many people will get this outcome? If we wrote this as, how many would you get right? Really, we're asking which one of these outcomes would you expect to get? And of course, the answer is 3, right? Because that's the most probable outcome. It's, to use the vocabulary in descriptive stats, it's the mode. It's the most probable outcome. So now we can ask a different question. Will everyone who guesses always get 3 correct? Now this is actually the same question really that I asked before. Will always be 3? No. We're talking about probability, random events. You won't always get 3, right? There's going to be a distribution. We know that. So this is getting back to that idea of variation, of standard deviation. Now, let's actually calculate the variation of this distribution. Right? We can do that. We've done that in the past for histograms, for data distributions. Well, really, probability distributions can be treated much the same way. And so what we can do, most simply, is use our fun 1var_stats function in our TI-84s. We're going to use L1 and L2 as our data set. You plug that into your calculator, and you get these results. And many of them, or at least the first one, is what we would expect. Actually, the mean is our expected value. Right? So that's going to be an important relationship to remember. Expected value is equal to the mean. Now I'll use the symbol mu. I think we talked about that earlier. Right? There are 2 symbols for mean. One is x bar, and one is mu. Right? This refers to the sample mean, or mean of a sample, and this refers to the mean of a population. Right? So this actually is an interesting point and is going to go into some of the curious values which are down here. Notice that we have our sample standard deviation is blank. We simply have no sample standard deviation. That's kind of strange. We have standard deviation, and notice what n is. N is 1. So there's an important question here. Well, n is, if we were talking about a data distribution, n is the number of data measurements. Well, why is n 1? I mean, we have a whole table here, like we used to have before. Why is n equal to 1? Remember how we would always get n before. N is the sum of our frequencies, which was usually an L2. All right? Frequency is the vertical length of our bars of our histogram. But recognize that really these aren't frequencies anymore, because this is not a data distribution. This is a probability distribution. So these are probabilities. And if we talk about adding up L2, well, this goes right back to our discussion of sample space. If this is the sample space, it's complete. These are all possible outcomes, all the possible outcomes. Then these are all the possible probabilities. So if you add up all the possible probabilities, what should it add up to? 100%. Well, this is percent. What's 100% as a decimal number? Is 1.0. Well, that's what n is. And that also is why we don't have a sample space, or a sample standard deviation. Right? If this is all possible outcomes, then this is population. This isn't a sample. Right? There is nothing outside of this table. So, and if you remember, if you calculated the sample standard deviation, the denominator was n minus 1, wasn't it? 1 minus 1 is 0. You can't divide by 0. So that's why it's left blank. And we only have our population standard deviation. And that's why up here for expected value, I use the population notation of mu. So when we are dealing with probability distributions, we actually are really dealing with population, because we have everything, and that's assuming you actually have the entire sample space. And that's actually can be a test, right? If you add all these up, does it equal 1? If it doesn't, then perhaps you left something out. So that's a nice test, and means we can write out a very important law, which is the law of probability distributions. I decided to get a new page because there just wasn't enough space down by the other one. The sum of the area under the probability distribution always equals 1. We're going to be using that a lot later on. And hopefully makes some sense looking at the probability distribution. If all of these numbers, let me switch colors. If we were to add up all those numbers and we know that equals 1, well, these numbers are the heights of all of these columns. Then that area is equal to 1.